Welcome all. In this video, I'll be discussing what is an ideal gas, what is a real gas, then uh, when this real gas behaves as an ideal gas, then compressibility factor, then Vander Walls equation, and what is the origin of Vander Walls equation, and what is critical isotherm, what is critical temperature, and critical conditions for Vander Walls equation. All these things I'll try to present in a very neat manner. And this video is very important for those students who are appearing for GATE examination with mechanical engineering, XE engineering sciences, which is very important, and then those who are preparing for engineering services examination. In fact, many students requested me to derive the equation, but today what I try to do is, it's not just that simply I am going to give you some equations. For everything, I will try my level best to give logical reasoning and concepts behind those equations. It's not that simply I'll be giving you the equation of Vander Walls as a P plus A by V square into V minus B is equal to RT. Nah. Where from that equation came, how the correction factors are coming, then what is compressibility factor, and I will try my level best to give everything in a crystal clear manner. Okay, fine. You know, according to kinetic theory of gases, KTG, I repeat, kinetic theory of gases. Dear students, you just observe here, it is a theory. It is a theory. Kinetic theory of gases. The first it says is no force of attraction. No force of attraction between molecules. Very good. This is the first assumption. No force of attraction or repulsion between molecules. Second, the volume occupied by molecules is negligible compared to, I repeat, everything will be explained in a detailed manner. The volume occupied by molecules is negligible compared to volume of container in which the gas is taken. Wonderful, sirs. Excellent. Now the question comes to my mind is, ये तो ideal है, sir. Ideally, if you are Sadguru Sadhu, you will not be attracted or maybe there is no attraction, there is no repulsion. Shant Swabhav. No attraction, no repulsion. Sadhu Swabhav. Ideal. But we are human beings. We are real human beings. There will be attraction. There will be repulsion. Repulsion का मतलब angry. Attraction का मतलब पास में लाना. So real gases. So definitely you don't find any ideal situations. All gases are real gases, but at times they behave as an ideal gas. So these two assumptions are in question. They are straight away in question. So definitely whenever there are molecules, you just see, my dear students, can you liquefy gases? What do I mean by liquefying gases? So gases, generally they occupy large volume. The molecules are very far. So if you increase the pressure, you can bring them close, and you can liquefy the gas. So when you are liquefying the gas, that means that liquid will occupy some volume. So definitely gas is also occupying some volume. So you cannot neglect the volume. इसका मतलब है, अरे कुछ gas का volume है, तो molecules they possess some volume. So when you are compressing, increasing the pressure, that gas is converted into liquid. You can liquefy the gas. So whenever you are liquefying, so whenever there is a liquid, means it is occupying some volume. Means definitely you cannot create na. Already kuch tha. Therefore you are getting something. Means I cannot neglect volume of the gas. तो ये भी question में है, sir. So I cannot neglect the volume of the gases. Definitely molecules possess. So according to kinetic theory of gases, the molecules are assumed something like point masses. So for example, observe clearly. For example, these are ideal gas molecules, so like point masses. And what you do is, this is the volume of the container. You bring all molecules together. सारे molecules को एक साथ लाओ. Okay. So देखो, and all molecules I brought at one place. And you know, according to kinetic theory of gases, The volume occupied by these molecules is negligible compared to the volume of container. ठीक है, sir. So I can say that what is the free space available? If the volume of molecules is very, very small, what is the free space available? It is equal to volume of the gases. Volume of the container. I repeat, volume of the container. But actually, molecules are something like solid spheres. So if you, my dear students, if you take this and if you keep all at one place, definitely it is occupying some volume. So actual available volume is less. So therefore, these two, and whenever you have molecules, there is a force of attraction, there is a force of repulsion. So these two are not correct. Now we were using the equation PV is equal to MRT or PV is equal to NR bar T. Arey yaar, suno carefully. Whenever I use mass, it is gas constant, characteristic gas constant. Whenever I use number of moles, it is universal gas constant. So either way, I can use no problem. Moles या फिर mass, कोई दिक्कत नहीं sir. It is universal gas constant, which is 8.314 kilojoule per kilomole per Kelvin. And this R is characteristic gas constant, which is R bar by molecular weight. So every gas has a different molecular weight. Therefore, characteristic gas constant R is different. Chalo, no problem at all. There is no problem. Ab dekho. But this is derived from kinetic theory of gases. That is, this is ideal gas equation. With what assumptions we have derived? No forces of attraction, no force of repulsion, and then the volume occupied by molecules is negligible compared to volume of container. Excellent, sirs. But actually, it's not like that. Listen carefully. Listen carefully. So, you know, my dear students, first let us think of this. So, I will take the equation which is PV is equal to NR bar T. Now, today we'll see with reasons why at low pressure and high temperature, the gas is behaving like an ideal gas with all physical explanation. And kindly, it's a request to all of you, you please, it may be a bit lengthy, 1 hour, 1.5 hours, whatever it may be, but please watch till the end. You are going to receive something best. Chalo. Now, my dear students, this is under ideal conditions. That is, volume occupied by gas molecules is negligible compared to the volume of container. There is no force of attraction, but actually there is a force of attraction. When there is a force of attraction, you need to correct this term. When there is a force of attraction, you need to correct this term. And you know, when the volume occupied by molecules is larger, it's not negligible. It is not a point mass. So they have some volume. So you have to take that into consideration. Means you need to correct this volume also. Therefore, when you correct pressure, when you correct volume, you get the equation for real gases. And that we call it as Vander Walls equation. So the best equation I feel is for real gases. There are so many equations, but I think Vander Walls equation is mostly used. So let's see in detail with derivation. With derivation. Ab dekho. Now I'll go for the term volume correction. Volume correction. My dear students, volume correction. Let us take this ideal case. Ideal is a point mass. Let this be volume of the container. Let this be volume of, this is ideal. So you know, so if you so what I'm doing is in ideal, so I repeat. So what I do is, this is ideal. This ideal. I'll bring, this is the volume of container. I'll bring all these to one place. When I bring all these to one place, as it is a point mass, which is an assumption, this volume is negligible. What is the free space available? Which is equal to volume of the container. Therefore, whatever V you are writing, volume of the gas is volume of the container. It's actually how much gas can spread freely. Freely, how much it can move. Freely, how much it can move. For example, it's something like this. You have a room. In room, you have a table. You have, what I say, क्या बोलते, chair है. So, I cannot move in that space. So whatever the space is available, I can move in that space only. But in ideal gas, kinetic theory of gases, those, whatever we know, the space is very small, therefore we have taken equal to this. But actually, it is like this, my dear students. Actually, they are like something like this, something like this. So can I neglect this? No. So how can I say this volume free space? Dekho, this is the free space. The free space in this is almost or exactly almost I would say equal to volume of the container because it is a point mass. Now सबको एक जगह ले आओ. Bring all to one place. Bring all to one place. Yes. Let's say I brought all this. This is the free space available. So for real gases, the free space available is less. तो क्या करना चाहिए सर? What will be this, sir? What will be this? This I can write. If 1 mole is occupying B space, if 1 mole is occupying B space, and if there are n moles, the total this is NB. So effective, whatever you are getting, the free space that you are getting, like this, in this case it is V. But as if 1 mole occupies B volume, n moles, if there are n moles will occupy n into B. So this is NB. So therefore, what will be the volume now? This total volume may say, total volume of the container may say, you remove this, and that is known as the available space, available space. Therefore, there is a need for us to correct. Why do we need to correct? Because it's not a point mass. It's not a point mass. They are like rigid spheres. So please note down that this NB is known as co-volume or excluded volume. NB. Why is this taken? Because gases occupy volume. Molecules have a definite volume. It's not a point mass. Therefore, this is the volume available. This is the volume available. This is the volume available. So this is correction that we have to see. So can I write, my dear students? Either the gases. Dekho, please observe carefully. This is the volume now. So I should write. Aram se dekho. Can I write V real? This is the real. Is less than V ideal. V real. Dekho ek baar. So इसके comparison में V means the space available. Space available. Therefore, please understand carefully. अगर understand carefully. Therefore, now because it is occupying some volume, it is occupying. Therefore, I need next space available will be this one. So therefore, we have corrected. So V place में क्या लिखना चाहिए? Here it is V of the container, but here it is V minus NB. So in case of real gases, I should not write V, but I should write V minus NB, where B is known as co-volume or excluded volume. Chalo, ye to ho gaya, sirs. This is over. Is it clear, my dear students? So whatever the effective is available, that we have to take. Here, effective available is, as the volume is very, very small, effective available will be equal to container, where effective available will be remove this space, and then you get this available space. Leave it. No problem at all. Now, we need to correct pressure. What is the reason for correcting pressure, sirs? What is the reason for correcting pressure? Because there are forces of attractions, which kinetic theory of gases neglected. For example, idhar dekhna. Listen carefully, my dear students. Listen carefully. Now, let us take ideal gas. Let us take ideal gas. Now, in ideal gas, what is that you have assumed? No force of attraction. It's something like this. Ideally, you are preparing for gate. For example, you are here. Listen, ye aap hai. Ideally, you are preparing for gate. It means there are different molecules. Means your friends, your relatives, they don't care. If you are ideal you are preparing. Ideal ki baat kar rahe. You don't care. Your target is what? Gate. This is gate. मतलब wall is equal to gate. So you straight away hit this. So therefore, in case of ideal gas, whatever the pressure is there now, it is because of this molecule hitting, and there is no force of attraction. This molecule is not pulling it. This molecule is not pulling this molecule. So therefore, it hits. The target is only gate. Even though people are pulling you, there is no pulling force. You don't care. You have insulated from everything. Ideally, you don't worry about this. Therefore, you hit the target, and therefore you get first rank. High pressure se आप hit करेंगे. Very good. So this is ideal case. Ideal. So ideal pressure you are hitting. Now, observe here. Now you are hitting. देखो, this is gate. This is your target. Now you are hitting. रिलेटिव से तेरे से नहीं होगा, फ्रेंड्स से तू कुछ नहीं करेगा, एंड नेबर से तू कुछ नहीं करेगा. What is happening? This is the force of attraction. So in real case, there is a force of attraction. So are you hitting with the same target? No. So with what pressure you are hitting? Less pressure. इसलिए आपके marks less आ रहे sir. Because in real case there is a force of attraction. In real case there is a force of attraction. That's why it is hitting the wall with less pressure. So therefore I say this pressure is, देखो एक बार, P ideal is more, P real is less. फिर equate कैसे करेंगे sir? If you are equating, so P ideal, if I equate P real plus pressure correction factor. I repeat, if this is more, if something is more, if you want to equate, you have to add some term. This is known as pressure correction factor. Now let us see on what parameters does the pressure correction factor depend. Let's see, sirs. Look at carefully. You know, if the number of molecules, if the density is more, this attraction will be more. Yes or no? If the ये प्रेशर किस प्रेशर से हिट कर रहा है? If more, look at my dear students, this pressure correction factor depends on two things: force of attraction and then collisions. What do we mean by collision? Pressure is number of collisions per second. In fluid mechanics, I taught very clearly. Pressure is number of collisions per second. If the density is more molecules will hit this, thereby pressure will be more. So number of collisions are more means pressure is more. So it depends on density. I repeat, it depends on density. Collisions will depend on density. So if more molecules are colliding, if the density is more collision, more pressure. Similarly, if number of molecules are more, the attraction is also more. The force of attraction is also dependent on density. इसका मतलब the pressure with what it is hitting, it is depending on the force of attraction. It is depending on, if number of molecules are more, I repeat, if the number of molecules are more, the attraction will be more. अरे यार और थोड़े हैं. If the number of molecules are more, attraction force is more. When the force of attraction is more, means when the density is more, the force of attraction is more. Similarly, if more molecules are there, more molecules will hit, and thereby it will influence the pressure. So when more molecules hit, more collisions, means when are collisions more? When the density is more. When density is more molecules will hit. So therefore I can say this pressure correction factor is directly proportional to density. So density ka square, density. And you know, density is equal to mass by volume. If it is mass density, mass by volume. If it is molar density, number of moles. So pressure correction factor is directly proportional to, if I take molar, means number of moles per unit mass. So density can be written as number of moles per unit volume. What is mass density? Mass by volume. What is molar density? Moles by volume. But it is iska square hai, therefore it is square. So what will be pressure correction factor, sir? Pressure correction factor, I have to, if I have to remove this proportionality, I have to introduce a constant. So A n square by v square. So therefore, P ideal is equal to P real plus pressure correction factor. What is pressure correction factor? A n square by v square. इसीलिए ideal gas में जो pressure है ना, आपको ये substitute करना. That is P real pressure. P का मतलब real pressure plus real gas pressure plus a n square by v square. So therefore, अब मेरा equation, so this volume is v minus nb. Volume को v minus nb put करना, p को p plus a n square by v square put करना. So then you'll get the Vander Walls equation. So the beautiful Vander Waals equation is, my dear students, तो p के place में p plus a n square by v square into V minus NB, this is co-volume, and this is the term introduced for influencing force of attraction, is equal to NR bar T, and this is known as Vander Walls equation. This is the volume of real gas and this is the pressure of real gas, and this is known as Vander Walls equation, which is used for ideal gases. Wonderful, sirs. We have derived. Wonderful, sirs. We have derived. I request everyone to watch till the end. You are going to get something very beautiful with reasons. And if I take per mole, number of moles 1 ले लेना, P plus A by V square. If I take moles as 1 into V minus mole को 1 ले लेना is equal to mole को 1 ले लेना R bar T. I can. This is known as molar specific volume. क्योंकि per mole लिए. This is the equation. Very good, sirs. Very good. Now let us try to see one important term. ध्यान से सुनो, sirs. अब ये बहुत important है. So let me proceed. Now I'll introduce one term known as compressibility factor. Compressibility factor, that is Z. Let's see what is Z. And physically, I'll explain what is Z. Physically, let us see what exactly is Z. I request everyone, physically, I'll explain. Let us take a container. Let us take a container. Now, let the pressure be P, temperature be T, number of moles be N, and volume be V. Let it be an ideal gas. Let it be an ideal gas. And this concept is very, very important. Just listen, my dear students. Let it be ideal gas. Very good. Now, I will write, please observe that. You know, my dear students, this is ideal, but ideally is not existing. So we have to take real only. What you do is, for the same pressure, for the same temperature, and for the same number of moles, आप real gas को ले लेना. अरे यार, you have taken one ideal gas, that is, which is at a pressure P, and it is at a temperature T, the number of moles are N, and its temperature is T. अब एक काम करो, same pressure, same temperature, same number of moles, let's take real gas. And it is observed that it is not occupying the same volume. So it is occupying, sometimes it occupies less, sometimes it occupies more. I'll explain why sometimes it occupies less, sometimes it occupies more. Physically, I'll explain, don't worry. So therefore, this volume, I write it as ideal. And now, same pressure, same number of moles, same temperature. Now this is real. This is real. That means there is a deviation from ideal gas behavior. There is a deviation from ideal gas behavior. This compressibility factor is defined as, अगर दोनों compare करना है sir, let us say there is one gas, particular gas, oxygen gas. Say if I assume it to be behaving as an ideal gas, let the oxygen pressure be P, let the oxygen temperature be T, let the oxygen volume be V, let number of moles be N. Okay, let us assume it to be behaving as ideal gas. And actually, if you see the actual behavior for that particular temperature, for the same temperature, for the same pressure, for the same temperature, and for same moles, it is deviating from ideal gas behavior. And please find out volume real. This is observed volume. We call it as observed volume. So this real gas volume or observed volume to the ideal gas volume, we call it as compressibility factor. Because volume is something related to compression. If the volume is, you have studied in compressible flow, it is nothing but variation of volume or density. Okay, now this is known as compressibility factor and it is dimensionless. Now the question that comes to my mind is, I repeat sirs, तो एक काम करो sirs, for the same pressure, for the same moles, same temperature, see ideal volume. अगर वो ideal की तरह behave कर, अरे it's something like this way, it's something like this. सुनो carefully. If no one is there at home, you are alone at home. Ideally, आप क्या कर रहे हैं? जब तब कर रहे हैं. Ideally, तब जब कर ले, तब तब कर ले. This is ideal. But actually, there is no one at home. You are alone. Same situation, same house. What is your actual behavior? पता नहीं. That is the deviation from ideal. So real to ideal is known as compressibility factor. Wonderful, my dear students. Excellent, my dear students. No problem at all. So you know, my dear students, PV is equal to N R bar T. In R bar T. Listen carefully. So can I write this as, अगर ये किसके लिए applicable है sir? This is applicable only for ideal gas. This is applicable only for ideal gas. ये तो ideal के लिए है. So now you tell me, what is the ideal volume? What is the ideal volume? It is N R bar T by P. N R bar by P. तो put करो यहाँ पे. तो compressibility factor is equal to V real by V ideal. What is V ideal? N R bar T by P. N R bar T by P. तो ये V real and V ideal is nr bar T by P, nr bar T by P को ऊपर ले जाओ तो Z will be equal to PV real by nr bar T. This is very important equation. I'll take this equation, I'll proceed. So Z is equal to PV real by nr bar T. Z is equal to PV real by nr bar T. Excellent, sirs. No problem at all. Look at carefully. Now let us see what is the value of Z for ideal gas. And you know very well, अगर ये ideal की बात कर रहे हैं, and you know very well, so अगर वो ideal है, तो कौन सा volume occupy करेगा? My real volume is also ideal volume. अरे यार, if it is an ideal volume, if it is an ideal gas, so real volume is also, observed volume is also ideal gas volume. This real volume means observed volume. अगर वो ideal की तरह behave कर रहा है, if it behaves as an ideal gas, if it is behaving as an ideal gas, my volume real will be ideal volume, exactly. So therefore, ideal, I'm calculating for ideal gas, compressibility factor for ideal gas. So if it is ideal gas, volume will be ideal gas volume. V means real volume. If it is ideal, real will also become ideal under ideal conditions. So volume is V ideal by nr bar T. But everyone knows for an ideal gas, PV is equal to nr bar T. This is ideal gas. So can I write PV ideal as nr bar T? Excellent, sirs, by nr bar T. It means for ideal gas, the compressibility factor is 1. Very important. For an ideal gas, the compressibility factor is 1. And for real gases, we will be seeing now, it will be greater than 1 and it will be less than 1. अब पूरा reason के साथ देखेंगे. What does it mean, sirs? Physically, what does it mean? इसका मतलब ideal gas के लिए compressibility 1 है. इसका मतलब real gas is behaving like ideal gas. कब possible होगा, sir? Simple है. When the force of attraction and the force of repulsion, जब force of attraction, force of repulsion same होगा, तो what will be the net force? 0. Ideal gas का है. मतलब एक one real gas is behaving in such a way, if the force of attraction and the force of repulsion, if both are same, the net force will be 0, and which is similar to, means under real conditions, when are real conditions becoming ideal conditions? Under ideal conditions, there is no force of attraction. तो ये कब possible है, sir? देखो, in real there is force of attraction, there is force of repulsion. So if force of attraction and force of repulsion become same, then what is happening? Look at, if force of attraction and force of repulsion become same, there is no influence of force. When there is no influence of force, my ideal and real will become same. When ideal and real become same, Z will be equal to 1. That is the conclusion from here. Now observe here, sirs, and we have seen Z is equal to 1 means my real gas is approaching ideal gas behavior. When Z is 1, my real gas is approaching ideal gas behavior. Why is it happening? Because in that case, the force of attraction, force of repulsion, when they become same, net force will be 0. Thereby, even in ideal gas assumption, what is that? Net force is 0. वही तो आ रहा है. Now, let us take Z less than 1. What is Z, sirs? It is actually known as deviation from ideal gas. Whenever Z is moving from 1, maybe more than 1, maybe less than 1. Let us see the physical meaning of Z less than 1 and Z more than 1. So already when Z is 1, the force of attraction is equal to force of repulsion. So net force is 0. Let us say Z is. And you know, Z is nothing but V real by V ideal. Already we have seen V real by V ideal. Now let us take a case where case 2. Already case 1 we have seen Z1. Z1 का तो होगा. Case 2. Z less than 1. So what will happen? V real is less than V ideal. क्या मतलब है सर? रियल गैस का वॉल्यूम कम है. रियल गैस का वॉल्यूम कम है. It means the force of attraction is more. The force of attraction is more. That's why the volume is less. The force of attraction is more. So therefore, attraction is dominating. That's why the volume is less. That's why the real volume is less. When the force of attraction is more, I repeat, my dear students, when the force of attraction is more, what is happening? When the force of attraction is more, the volume is becoming less. The volume is becoming less. Similarly, attraction is more. Let us take Z greater than 1. And Z is V real by V ideal. What is this greater than 1? So V real is greater than V ideal. What does it mean? The real gas volume is more. When the real gas volume is more, means repulsion is more. Repulsion is more. Repulsion is more. Repulsion is more. Here, the force of repulsion is more. Force of repulsion is more. Force of repulsion is more. Excellent, sirs. ये कब होगा, sirs? Force of repulsion is more. Please understand carefully. Please understand carefully. Let me explain. Till now, we have seen what is compressibility factor. What is compressibility factor? And what is the equation of compressibility factor? देखो, it is PV real by NR bar T. The compressibility factor is PV real. So what is the significance of compressibility factor? It shows how far it is from ideal gas behavior. तो कितना deviation है? मेरा real gas, how much it is deviating from ideal gas? It is showing. Excellent, sirs. Now, please observe here. हाँ. Now understand carefully. Let's proceed. Now, this is Z can be 1, Z can be less than 1, Z can be greater than 1. अब देखते हैं सर कुछ critical temperature, all those things. Let us discuss in detail. तो hope there is no problem with this. चलो आगे बढ़ते हैं सर. Now, after that I'll be explaining liquefaction and how this Z is influencing liquefaction. All those we'll discuss in detail. इधर देखना सर. You know, my dear students, ध्यान से सुनो. तो देखो एक बार, P plus A by V square into V minus B is equal to RT. Let us try to find out the compressibility factor of Vander Walls gas, that is real gas, under different cases. Let's see what do we mean by different cases. अब ध्यान से सुनो. Please listen carefully. Case 1. When pressure is very, very low. When pressure is very, very low, low pressure. Low का मतलब low pressure. देखो सर, जब pressure ज्यादा होता है, when the pressure is more, volume will be less. When the pressure is more, volume is less. When the pressure is less, means volume is very large. I repeat, sirs, जब pressure ज्यादा है, देखो, I'll give you a simple example. When you are compressing it, when the pressure is more, when you are increasing, what is happening to the volume? Volume is becoming less. So when the pressure is high, volume will be less. When the pressure is low, now please observe here, let this expand. जब ध्यान से सुनो, जब वो expand होते जाता है fast में, तो क्या होगा? Pressure will decrease. Understand carefully. So therefore, when the pressure is very, very low, what is an indication or what is the consequence? When the pressure is very, very low, generally volume is large. Generally volume, देखो यहां पे शब्द देखो, pressure is very, very low. Pressure is very, very low. Volume is large. अरे यार, when pressure is high, volume is less. When pressure is low, volume is large. When volume is large, what is V square? It will be very large. What will be V square? It will be very large. What will be V square? It will be very, very large. Very, very large. तो डिनोमिनेटर में है सर ये, डिनोमिनेटर में लार्ज क्या होता है, तो ये टर्म क्या होगा? आई रिपीट, व्हेन द प्रेशर इज वेरी वेरी लो, वॉल्यूम इज लार्ज. व्हेन द वॉल्यूम इज, सी आई एम कैलकुलेटिंग compressibility factor of Vander Walls gas under different cases. I'll be discussing 3 to 4 cases. We have to discuss those cases are very very important. If the pressure is very very low, volume is large. When the volume is large, V square is large. When V square is large, denominator में है, तो something by large, negligible. Very useless fellows. 3 by something, 4, 5, 6, 7, 8, 9. Very large. तो negligible होगा. ये negligible होगा. P. And you know, सुनो carefully. सुनो. When V is very large. What will be B, sir? Compared to V, V is very large. V के कंपैरिजन में V is large, B के कंपैरिजन में V is large, तो neglected. क्या आ गया सर ये? P is equal to RT, ideal gas. Ideal gas. For ideal gas, what is P is equal to RT हो रहा है. At low pressure, my real gas is converted into ideal gas. So therefore, compressibility factor will be equal to 1. At very low pressures, the compressibility factor is equal to 1. Means an ideal gas a real gas behaves as an ideal gas under very low pressures. What is the physical explanation for this? When pressure is very low, the volume occupied by gases is very large. When the volume is very large, देखो, when the volume is very large, the intermolecular दूर है, the force of attraction is negligible. आप यहाँ पे अमेरिका में आपके friend, attraction is negligible. So when pressure is very low, the volume occupied by these gases is so large and the molecules is so large, and thereby the force of attraction is negligible, which is tallying with kinetic theory of gases. Next, when the volume is very large, the volume occupied by gas molecules is negligible compared to the volume of the container or volume occupied. So therefore, both are tallying with kinetic theory of gases. That's why a gas behaves as an ideal gas under low pressure irrespective of temperature. यहाँ पे temperature का कोई जिक्र नहीं आया. I have not made any mention of temperature. Irrespective of the temperature, at very low pressures, forget about temperature. No matter what the temperature is, तो जब भी प्रेशर बहुत कम होता है, very low, physical explanation I have given, it behaves as an ideal gas. Absolutely fine. अब एक दूसरा केस ले लेंगे. This is case 1 when the pressure is very low. Great. Next, case 2. When the pressure is low. Listen carefully. Low का मतलब not that low. Low का मतलब not that low. It's low. तो P plus A by V square into V minus B is equal to RT. Pressure is low, not that low. So therefore, understand carefully. Please observe. Low है लेकिन उतना लो नहीं है. तो all terms will be there. Pressure is low means volume is large but not that large. Unlike previous case pressure was very low. So that's why volume was very high. We neglected this. When volume was very high, it was this is very small, so we neglected. But now none of this can be neglected. This is the real volume, sirs. This is the real volume. अब देखो, what is Z, sirs? It is PV real by NR bar T. देखो, it is the real volume. देखो एक बार, already I have given. Just observe. PV real by NR bar T. So PV कहाँ गया? PV real by. This is the real volume. This is the real volume because it's a real gas equation. Okay. क्या करो, sirs? I'll do one thing. None of this can be neglected. P plus A by V square. Is equal to RT by V minus B. No problem at all. Wonderful, sirs. But actually, if you understand very cautiously, if you see this term very cautiously, my dear students, आराम से देखो. Is equal to P plus A is equal to RT by B. Excellent. No problem at all. अब देखना, sirs. एक काम करेंगे हम. P can be written as RT by V minus B minus A by V square. No problem. What do you want? Compressibility. तो क्या करो? P है यहाँ पे, V by NR bar T से डिवाइड करो. V by NR bar T. अरे यार, if you take n as 1, in this equation I took n as 1. Actually it will be n square V square NB. तो n मोलार मतलब एक मोल ले लेंगे. So therefore, let me take n as 1. If I take n1, this will be the equation. Okay, no problem at all. कोई problem नहीं, sir. So this will be specific molar specific volume. Hope you understood. Per mole we'll calculate. So divide with क्या करो? Multiply with V real by RT. इधर देखो. Same equation. Both sides. P is equal to
RT by V minus B minus A by V square. Both sides you multiply with same equation, V by RT. V real by R bar T. multiply with V real by R bar T. ये सब V real ही है सर, V real by R bar T. But what is PV real by R bar T? So same equation, in order to find out compressibility factor, I'm multiplying with V by RT, V by RT, V by RT. And V is V real volume only. So sometimes I'm writing V real, sometimes I'm not writing, it's a real volume only. Okay. So what is PV real by RT? Compressibility factor is equal to, multiply करो, क्या होता है, RT गया तो V by V minus B minus A by V, अरे minus A by V. Excellent sir. So I think I can write this as, look at carefully, I think I can write this as 1 by 1 minus B by V. Excellent sir. Can we write 1 by 1 minus B? अरे V common ले लो तो yes. Okay. Can we write, I will take this to next slide. I will take this to next slide sir. Z is equal to 1 by 1 minus B by V minus A by V. Excellent. So can I write this as 1 minus B by V power minus 1? अरे 1 by x is x power minus 1 minus A by V. Okay. Z is equal to 1 plus, you know very well, what is 1 minus x whole power n, 1 plus nx, binomial expansion. So it will be 1 minus of minus a इधर आएगा, अरे यार 1 plus x whole power n, 1 plus nx plus n into n minus 1 by 2 factorial x square plus so on so forth. Simple mathematics. तो minus of minus plus b by v plus b square by v square. So generally volume, pressure तो low है, I have not neglected V. Pressure तो low है sir, but what will be volume? High. But V square क्या होगा? 1 plus B square by V square. तो volume is large. When volume is large, V square terms, higher order terms can be neglected. Higher order terms can be neglected. Minus A. I'm neglecting higher order terms क्योंकि denominator में by V square, by V cube, those terms will come. So what is our case? Pressure is low. When pressure is low, volume is large. When volume is, समझ गए? Okay. So V square higher order terms are neglected. So therefore minus A by V. So 1 plus 1 by V into, कहाँ गया रे? 1 plus B by V minus A by, कहाँ गया रे? Minus A by V ना? Is it correct? Yes. Minus A by V. B minus A. It should be correct ना? So we have not committed any calculation mistake ना? देखो एक बार. P is equal to RT by V minus B, A by V square. Correct? RT. तो V by RT. तो V by RT. RT by V minus B, A by V square. तो V by V minus B. V कट गया. तो यहाँ पे RT है सर. वही तो मिस्टेक है. A by V minus B. RT is gone. This V is gone. A by V. RT is there. We forgot. RT, we forgot. That's what. RT. Therefore, this is RT. This is RT. We forgot. So, what will happen? 1 by V. 1 by V by RT. इसका मतलब क्या हो रहा है सर? This is the value. Means 1 plus something, compressibility factor is greater than 1. Now, let us talk about certain, let me give some graphical analysis. कुछ graphs करेंगे. Likewise, you can find out the compressibility factors under different situations. कुछ analyze करेंगे सर. और एक बात है सर. Now you tell me, please understand. कहां गया रे? Experimentally क्या किए? कुछ graphs find out किए सर. On this axis they took pressure. On this axis they took compressibility factor. तो यहां पे compressibility factor is 0. For ideal gas, what is the compressibility factor? 1. So therefore, no matter what the pressure is, the Z is equal to 1. So whenever Z is equal to 1, it is for ideal gas. Excellent. Now, my dear students, it is observed that, अब मैं कुछ logically बताऊंगा सर. It is observed that, बहुत logically बताऊंगा, सुनते जाना. तो shall I remove this sir? क्योंकि compressibility factor अब मैं यहां से शिफ्ट करूंगा सर. ओके, कोई बात नहीं. सो ग्राफ को हम एक सेकंड Let me explain in a detailed manner. Let me explain in a very, very detailed manner. देखो, this is the pressure and 0, 0, and this is the compressibility factor, which is Z is equal to 1 on this axis Z. So Z can be more than 1. It cannot be negative. How? Volume of what is compressibility factor? Real volume by ideal volume. Volume cannot be negative. So it is positive, but it can be less than 1. It can be less than 1. It is positive only. Okay. तो ये तो होगा ही नहीं, 0 है ये, compressibility 0 है, तो origin ये है. एक second. Let me erase this. Excellent, sirs. Excellent. No problem. This is the situation. Now, this is Z1 का मतलब ideal gas. अब देखो. Now I'll explain very clearly. Now, what they have done is they took one gas. मतलब आप gas को change नहीं करेंगे, sirs. Now we will not change gas. We'll take the same gas at a different. एक काम करते हैं सर, सेम गैस, कीप द टेम्परेचर कांस्टेंट. मतलब एक्सपेरिमेंट करो, whatever I'm giving you, I'm giving from experiments, but physically I'll explain also. Let us take temperature as some 35 Kelvin. अरे some temperature यार, you take some temperature. So I write this as, एक second please, I write this as some T1. So I have taken one gas. I repeat, my dear students, I have taken one gas. What is that I am doing? I am changing the pressure. So compressibility factor will change. But I am not changing temperature. I am not changing the temperature. Isothermal, मतलब same temperature लेके करेंगे. It is observed that, look at carefully. Something like this. ऐसा क्यों आ रहा है? I'll explain. And I'll change the color. This is for temperature. This is for temperature T1. This is for one particular temperature. So what we are doing is, gas is same, but we are changing temperatures. I repeat, sirs, gas is same and changing the temperature. I repeat, gas same है, temperature change हो रहा है. We'll take, देखो एक बार. Something like this. एक second, please. एक second, please. We'll take this color. I will explain physically, sirs. Don't worry. I'll explain physically. Color कौन सा ले लेंगे? अब देखो. Now I'll take some other temperature. Let us say this is T2. Let us take T2. Now, listen carefully. Please observe. Now, we'll take some other temperature. This is T3. आराम से देखो सर. We'll take some other temperature. T4. Now, the observation here is, what is your observation? Please listen carefully. Which one is deviating more? Observe here. The Z is equal to 1 means ideal gas. Which one is deviating more? You just see T1. Observe, my dear students, you just see T1 वाला. You see T1. इधर देखो. So much of deviation from this line, इस line से this much of deviation. देखो Z से. Oh my God, huge deviation. फिर deviation for T1. And if you observe, my dear students, for T4, just see T4, almost close. So it is observed that which one is close to ideal gas behavior? जिसका Z ideal से close है. So I can say T4 is close to ideal gas. Let us see what is the temperature of T4. Answer सुनो सर. It is observed that which one is deviating more? किसका deviation ज्यादा है? T1 का deviation ज्यादा है. T1, उसके बाद T2, उसके बाद T3. देखो deviation का मतलब क्या है? आइडियल से, देखो आइडियल से व्हाइट वन इज वेरी फार, ग्रीन व्हाइट से थोड़ा कम है, दिस ब्लू वाला यस उस इससे कम है, एंड T4 इज वेरी मच लेस. नाउ अंडरस्टैंड केयरफुली. इट इज ऑब्जर्व दैट टेम्परेचर्स आर लाइक दिस. Oh my God. यहां से I am going to bring some beautiful conclusion. It is observed that the temperature T4 is very high. So if the temperature is very, very high, it is coming closer to, my real gas is coming closer to ideal gas. See the deviation. बहुत कम है sir. बहुत कम है. See the deviation, sirs. See the deviation. Wonderful, sirs. So what is the physical explanation for this? So at high temperatures, gas can behave as an ideal gas. See this T4, which is very high. When the temperature T3 is T4 से कम है, deviating more. When T2 deviating. Look at sirs. Please observe clear. एक second please. एक second. आराम से sirs. आराम से मैं अभी बताता हूं sirs. एक second sir. Please sir. Okay sir. It will be like this. Okay. This is T2. Excellent sirs. Now understand carefully. जिसका टेम्परेचर ज्यादा है, it is behaving like an ideal gas. Now I want to give you the physical explanation. Already we have seen that at low pressures, I had explained, at when the pressure is very, very low, it behaves as an ideal gas. एक बार देख लेना sirs. Just you see from the graph. When the pressure is very, very low, this is the pressure. So pressure is decreasing. Pressure is very low. So it is close to ideal gas. And at zero pressure, all are coinciding. Means for all are starting from here. So देखो एक ऐसा. So for all at zero pressure, it is ideal gas. Means when pressure is very, very low, all are behaving like an ideal gas. I had given the physical explanation also. So low pressure pe, it is behaving as an ideal gas. But even at high temperature, it is behaving as ideal gas. Let's see what is the reason for this. जब टेम्परेचर ज्यादा होता है, ऑब्जर्व केयरफुली, व्हेन द टेम्परेचर इज वेरी वेरी हाई, यू आर गिविंग काइनेटिक एनर्जी टू मॉलिक्यूल्स. व्हेन यू गिव काइनेटिक एनर्जी टू मॉलिक्यूल्स, दे मूव फार अवे. व्हेन दे मूव फार अवे, दूर जाएंगे, देयर इज नो फोर्स ऑफ अट्रैक्शन. मींस माय काइनेटिक थ्योरी ऑफ गैसेस इज होल्डिंग. एट हाई टेम्परेचर, जब टेम्परेचर बहुत ज्यादा होता है, तो मॉलिक्यूल्स के लिए दे गेट काइनेटिक एनर्जी, एंड यू नो काइनेटिक एनर्जी इज द मेजर ऑफ टेम्परेचर ओनली. देखो, so when the temperature is very, very high, they move far, expand हो जाएंगे, दूर जाएंगे. When they move far, there is the force of attraction is negligible. When the force of attraction is negligible, it's like ideal gas. So जब दूर जाएंगे, the volume occupied by gas is so large, so therefore means it is almost equal to, मतलब जब volume occupied by gases will be small compared to the volume that they are occupying. So therefore the gas behaves as an ideal gas. Not only at low temperature, but also at high temperature. ये बहुत important है sir. What is the physical explanation for this? At low pressure, when the pressure is very, very low, it means when can I make pressure? देखो, pressure बढ़ा रहा हूं तो volume कम हो रहा है. Pressure is low, volume occupied is large. When volume is large, attraction forces are negligible. Similarly, when the temperature is large, they expand. When they expand, the force of attraction is negligible. That's why a gas behaves as an ideal gas under low pressure and high temperature conditions. Vander Walls से भी वही निकला. देखो, Vander Walls से भी वही निकला sir. Now understand carefully. अब बहुत logically पढ़ेंगे. Look at now. Let's go to critical state. Now अच्छा points पढ़ेंगे sir. Now critical pressure and critical temperature. This is very important. Critical pressure and critical temperature. Look at carefully. आराम से देखो sirs. You know, my dear students, please understand carefully. Let us take volume here and let us take pressure here. there is one term known as liquefaction of gases. Means conversion of gas to liquid. Liquefaction of gases. Wonderful, sirs. Look at carefully. There are two ways to liquefy a gas. First one is increase the pressure, keep the temperature constant. This is the first method. Increase the pressure, keep the temperature constant. The second one is keep the pressure constant and decrease the temperature. दो तरीके हैं सर. So how can I liquefy the gas? Very simple, sirs. एक काम करो sirs, काम करो. In a piston cylinder arrangement, keep the pressure constant and slowly you cool it. When you are cooling it, the molecules will come closer and it becomes liquid. Similarly, for the same temperature, now you increase the pressure. When you are increasing the pressure, देखो, in liquids, molecules are closer. In gases, they are very far. I repeat, sirs. In liquid, molecules are closer. In gases, they are very far. So if I increase the pressure, they come closer. Means they are coming towards liquid. So I can increase the pressure or I can decrease the temperature. So let us take the first one. एक बार first वाला ले लेंगे, sirs. Let's take the first one. Increasing the pressure and keeping the temperature constant. At constant temperature, इधर देखो. Now, look at, I am increasing the pressure. So when I'm increasing the pressure, what is happening? Volume is decreasing. देखो, when I'm increasing the pressure, the volume is decreasing. Yes. At some point, now the liquid will be available. अब ये गैस क्या करेगा? हम कंप्रेस कर रहे हैं, तो प्रेशर बढ़ रहा है. Pressure is increasing, volume is decreasing. So at some point, my liquid starts converting into, my gas starts converting into liquid. So therefore, अब क्या होगा, sirs? Please understand carefully. You know that phase change occurs at constant pressure. अब देखो, अब पूरा गैस लिक्विड में कन्वर्ट हो गया. Now this is complete liquid. अब उस लिक्विड को कंप्रेस करो, you will be seeing something like this, almost vertical. What is the reason for this? Because liquids are generally incompressible. So even though I am increasing the pressure, the volume is almost constant. ये पूरा गैस ये लिक्विड शुरू हुआ, लिक्विड गैस and it is liquid. Now my dear students, now you repeat this experiment for this is one particular temperature. ये एक particular temperature है. This is one particular temperature. Now you increase. So let us say I have carried out this at some 200 units of temperature. Now I will increase the temperature. अरे ये एक isotherm है sir. I increase the temperature. तो क्या होगा? So now it is observed that, please understand carefully. So if I am increasing the temperature, observe. So the pressure at which, ध्यान से सुनो, let us assume that at this pressure, for this temperature, at this pressure, my gas started liquefying. So it is observed that as the temperature is increased, T2 ज़्यादा है sir T1 से, so it is not liquefying at the same pressure, but it is liquefying at a pressure higher. Let's see the reason for that. तो जब आप टेम्परेचर को बढ़ा रहे, it is one more isotherm. When you are increasing the temperature, you need higher pressure to liquefy. What is the reason for that? When जब temperature बढ़ता है, तो molecular activity will be more. When the molecular activity is more, they are very far. जब temperature बढ़ रहा है, molecular activity is more. So that's why you need high pressure to bring them back. Close लाने के लिए, जब high temperature पर activity जब ज्यादा है, तो ज्यादा pressure क्लोज लाने के लिए रिक्वायर्ड होगा. दैट्स व्हाई एट हाई प्रेशर ये हो रहा है सर. नाउ लिक्विफेक्शन, इधर देखो यहां पे हो गया. अब सेम लाइक दिस. सिमिलरली अगेन यू इंक्रीज, अगेन इट इज ऑब्जर्व समथिंग लाइक दिस. अब एक काम करो सर, नाउ यू जॉइन ऑल दिस. आई रिपीट माय डियर फ्रेंड्स, नाउ यू जॉइन ऑल दिस. इट इज ऑब्जर्व समथिंग लाइक दिस. something like this. And this is your saturated liquid, saturated vapor, no problem at all. यहां पे क्रिटिकल पॉइंट, इसका फिजिकल मीनिंग क्या है सर? देखो एक बार ध्यान से सुनो. इफ यू सी दिस क्रिटिकल पॉइंट, मैं लाल शाही से बताऊंगा सर. सो एट दिस व्हाट इज हैपनिंग, इधर देखो, यस ऐसा हो रहा है सर. इट मींस यहां पे लिक्विड वेपर का कोई, इधर लिक्विड वेपर इज इन इक्विलिब्रियम, देयर इज नो लिक्विड वेपर इन इक्विलिब्रियम. इट मींस at, इसको क्रिटिकल टेम्परेचर बोलते हैं. दिस टेम्परेचर आई कॉल इट एज क्रिटिकल टेम्परेचर. सो व्हाट इज क्रिटिकल टेम्परेचर? इट इज दैट टेम्परेचर अबव विच liquefaction is not possible, above which it's not possible. ऐसा फिजिकली क्यों हो रहा है सर? फिजिकली बिकॉज when the temperature is very very high, critical बहुत ज्यादा है, तो it becomes virtually impossible to bring molecules closer. जब liquefaction का मतलब molecules को close लाना, जब टेम्परेचर इतना ज्यादा होगा, very very high, so इतना ज्यादा एक्टिविटी होगा, so no matter what pressure is there, it's difficult to liquefy. That is my critical temperature. तो अब देखना सर, वेरी वंडरफुल सर. अब ये हो गया हमारा डायग्राम. नाउ वेयर इज द गैस? अब मैं एक नया डायग्राम ले लूंगा सर. लेट मी टेक अ न्यू डायग्राम. लेट मी टेक, अरे हमारा ग्राफ, हाँ आराम से, टेंशन मत लेना सर, पूरा पढ़ेंगे नीटली. नाउ वी हैव सीन समथिंग लाइक दिस. एक्सलेंट. तो ग्राफ आया था समथिंग लाइक दिस. Okay, at critical point, the isotherm is something like this. Dear students, at critical point, it is like this. इधर देखो, ऐसा रहा है सर. At critical point, it's something like this. I repeat, sir. At critical point, it is something like this. Something like this. Now observe. ध्यान से सुनो sir. This is the critical temperature. So now the question that comes to our mind is, where can I treat a gas as ideal gas? Low pressure. ये तो liquid vapor है रे, ये तो liquid and gas in equilibrium. It is liquid. It is only gas. So if you want to apply ideal gas equation, this is the favorable region. But where? Just now you saw low pressure. Low pressure means here the pressures are low, means this is the feasible region, sirs. This is the feasible region. Here the pressures are low. At the same time, I also said high temperature. High temperature. देखो, इससे ये temperature ज़्यादा, इससे ये temperature ज़्यादा है. It means high temperature. So therefore, high temperature, low pressure. So here we can apply. But now the question that comes to my mind is, how can we apply? Excellent, sirs. एक्सलेंट. इधर देखो, कहां पे ज्यादा प्रॉब्लम होगा सर? इस रीजन में. इट कैन नॉट बिहेव एज एन आइडियल गैस बिकॉज टेम्परेचर्स आर नॉट दैट हाई, बट प्रेशर इज वेरी हाई. एट हाई प्रेशर यू कैन नॉट ट्रीट एज आइडियल गैस. सो देयरफॉर लो प्रेशर एंड हाई टेम्परेचर्स. देखो यहां पे टेम्परेचर ज्यादा हो रहा है. नाउ लेट्स ट्राई टू फाइंड आउट द क्रिटिकल प्रेशर एंड क्रिटिकल टेम्परेचर फॉर Vander Walls gas. Please listen carefully. You know Vander Walls equation is P plus A by V square into V minus B is equal to RT. Molar की बात कर रहे हैं, RT. Okay, no problem at all. Per mole. Okay. So I want to find out everything at critical. इधर देखना. This is my PV diagram. So actually if you see the critical isotherm, it is like this. इधर देखना. शेप देखना सर, शेप देखना. द शेप ऑफ दैट इज, तो वेयर आर यू फाइंडिंग आउट सर? क्रिटिकल पे. अब इसको लिखूंगा क्रिटिकल प्रेशर. व्हाट डू मीन बाय क्रिटिकल प्रेशर? एट दिस पॉइंट व्हाट एवर द प्रेशर इज देयर, क्रिटिकल प्रेशर. ये जो आइसोथर्म है, इट इज क्रिटिकल टेम्परेचर. दिस आइसोथर्म क्रिटिकल टेम्परेचर. ओके, नो प्रॉब्लम एट ऑल, नो प्रॉब्लम एट ऑल. इधर देखना. अब देखो, तो वीसी क्रिटिकल वॉल्यूम, वॉट एवर द वॉल्यूम इज देयर वी राइट इट एज ऑल दिस क्रिटिकल. ये क्रिटिकल वॉल्यूम, क्रिटिकल प्रेशर, क्रिटिकल पॉइंट पे क्रिटिकल प्रेशर, क्रिटिकल वॉल्यूम, एंड दिस टेम्परेचर इज क्रिटिकल टेम्परेचर. क्रिटिकल वॉल्यूम एंड क्रिटिकल टेम्परेचर. नो प्रॉब्लम एट ऑल, नो प्रॉब्लम एट ऑल. एक्सलेंट सर्स, वंडरफुल, वंडरफुल माय डियर स्टूडेंट्स. इज देयर एनी प्रॉब्लम? Is there any problem? Absolutely no problem. Now, please understand the mathematical analysis at this point. If you see that red curve, ये critical point है sir. ध्यान से सुनो. This is my CP, that is critical point. I'm just showing this point. Actually, you have this liquid curve and vapor curve. No problem. देखो, ये point है यहाँ पे. Point है यहाँ पे. Critical point. So if you see that graph, it is like this. Either देखो, if you see that graph, see, my dear students, it is becoming horizontal and then it is becoming like this. When it is becoming horizontal, what is the slope? 0. I repeat, this is becoming something like this. देखो इधर, it is becoming something like this, horizontal और ऐसा आ रहा है. So when it is becoming horizontal here, at the critical point horizontal, horizontal का मतलब slope क्या है सर? 0. That is dou P by dou V. Where is this occurring, sirs? Where is this occurring? Why? Because temperature is constant. When you have this is isotherm. Isotherm means temperature is constant. Whenever some parameter is constant, it becomes partial. Whenever you are differentiating by treating one parameter constant, it is different, it is partial. So therefore, ये isotherm है. Means here temperature is constant. It is critical isotherm. Critical isotherm. So that's why I wrote partial. So what should be the value here? 0. Why it is 0? Because the slope is 0. Because my isotherm is becoming like this because the slope is 0. And my dear students, this is also the point of inflection. Sir, ये समझ में नहीं आया inflection. इधर देखो. If you observe, my dear students, अगर ये continue होता, it will be something like this. अगर ये continue होता, it will be something like this. It means at this point, it is not following this. It is following this. Means concave upward say, मेरा shape, actually it was concave upward up to this. Concave upward. यहां आने के बाद concave down हो गया sir. So please observe here. यहां तक it was concave upward. यहां तक it was this portion. It was this portion concave. This is cave upward. But yahan aane ke baad, it is becoming like this. This is my curve. So it is becoming concave downward. So from calculus mathematics, at the point of inflection, which is nothing but concave upward se concave downward change hota hai. When it is moving from concave upward to concave downward, my mathematics says the second order derivative is also 0. This is actually coming because the slope is 0. And this is coming because the curvature is changing from concave upwards to concave downwards. Concave upwards से concave downward आने के कारण ये shape change हो रहा है. That's why calculus mathematics बोलता है at the inflection point का मतलब क्या है? Means concave upward से concave downward और concave downward से concave upward. Means इधर से इधर या इधर से. Whenever such thing is happening, the second order derivative is 0. मेरे पास इक्वेशन रेडी है. 2 conditions apply करना, will do it. Don't worry. So have you understood the reason why the first order is 0, second order is 0? Slope is 0, therefore this is 0. And at inflection, ये curvature change हो रहा है upward concave से. ये देखो, ये upward concave है, ये downward. So this is downward, this is upward. That's why whenever the curvature is changing, we use this. So second is 0. अब ये equation लेके 2 conditions apply करेंगे sir. Now we'll take this. Listen. हो गया sir. Now everything is that is at where at critical point, sir. Why? At critical point the slope is 0. At critical point is inflection point. Therefore, second order derivative is 0. So therefore, P plus A by VC square a critical point पे into V minus B is equal to RT. T को TC भी लिख लेना, कोई चिंता नहीं है सर, कोई चिंता नहीं है. T is TC. Absolutely no problem at all. Wonderful, my dear students. इधर देखो. Now I'll do like this. PC plus A by VC square is equal to RTC by VC minus B. देखो, excellent sirs. Or this can be written as PC is equal to RTC by VC minus B, okay, minus A by VC square. Excellent. Now, can I write this as RTC into VC minus B power minus 1? इसको ऊपर ले जाओ. Minus A VC power minus 2. Yes, my dear students. Yes. Now, differentiate with respect to V. Dou P by dou V. देखो. Dou PC by dou VC is equal to, हाँ, RTC is constant. R is constant. TC का मतलब critical isotherm. What is X power? You are differentiating with respect to B is constant. So X power minus 1. n into x power n minus 1. So it will be minus 1 into vc minus b minus 1 minus 1. एक बार देखो, n into x power n minus 1. Excellent. So again you differentiate. vc का differentiation 1, b का 0 है. Minus, excellent. a times, इधर देखो, what is x power n? We are differentiating with respect to v. So x power n minus 2 into n into x power n minus 1. So it will be minus 2 vc power minus 3. Minus 2 vc power minus 3. And this should be equal to 0. Why this is equal to 0? Because slope is 0. आराम से देखो सर. So dou pc by dou vc is equal to rtc, of course, minus into vc minus b minus 2 minus 1 minus of minus is plus. I repeat, minus of minus is plus. 2a vc power minus 3 is equal to 0. ये एक इक्वेशन बन गया. Okay, so please listen carefully. Dou p by dou c 0. Okay, now observe here. तो जब ये 0 हो गया, तो you take, this is negative, this is positive, you take it to that side. तो क्या होगा सर? 2a by vc cube, 2a by denominator vc cube, ये उधर ले जाना, is equal to rtc by vc minus b whole square. Let me take this as equation number 1. बहुत इंपॉर्टेंट है. No need to by head, sirs. Let me take this as equation number 1. Excellent. What is dou p by dou c? ये वाला है सर. What is dou p by dou c? ये वाला. You take this and go to the next slide. You take this and go to the next slide. Dou p by dou c is dou p c. हो गया सर, हो गया. Don't worry. Dou pc by dou vc is equal to minus rtc by vc minus b. Dou p by dou c is minus rtc vc minus b power minus 2 minus rtc vc minus b power minus 2 plus 2a excellent, sirs. No problem. This is one. Now because of inflection, again differentiate करो इसको. Again you differentiate, तो क्या होगा? Minus rtc. Again you differentiate, तो n into x power n minus 1. Minus 2 minus 1 is minus 3 plus 2a into ये minus 3 इधर आएगा, minus 3 vc power minus 3 minus 1, and this should be 0. Second order is also 0. Okay, minus of minus is plus 2rtc by vc minus b whole cube. Okay sir, ये इसको उधर ले जाना. हाँ प्लस हो गया, तो ये minus into minus plus, तो plus into minus you take it to that side, plus into minus you take it to that side is equal to 6a by vc power 4. Let this be equation number 2. Now just take equations 1 and 2. कोई प्रॉब्लम नहीं है सर. एक बार इक्वेशन 1 and 2 ले लेना. 2a by vc cube, 2a by vc cube is equal to 2a by vc cube rtc by vc minus b whole square. rtc by vc minus b whole square. एक बार चेक करता हूं सर. 2a by vc cube rtc by vc minus b whole square. c minus b. Okay, correct. No problem at all. No. Divide करो this equation 1. You divide both. What do I get? अगर दोनों को डिवाइड करेंगे 2 by 1, equation 2 by 1, what do I get? एक बार चेक करते हैं. rtc is gone. तो what do I left? v minus b gone. तो ये बचा है 2 by, अरे I am dividing both. तो rtc gone. There is 2 here. तो this is gone. तो vc minus b, correct ना? vc minus b is equal to, this is thrice and this is 1. तो 3 by vc. Excellent. तो 2vc is equal to 3vc, multiply करो 3vc minus 3b, और 3b is equal to 3vc minus 2vc is vc. तो at critical point the critical volume is 3 times B. ये बहुत इंपॉर्टेंट है सर. For Vander Walls gas, VC is equal to 3B. Very very important. तो my dear students, let me try to, हाँ ये आ गया सर. अब A को कैलकुलेट करेंगे, कोई बात नहीं. So look at, you take any one equation. VC आ गया. तो RTC equation 1, RTC by VC minus B is equal to RTC by VC minus B, sorry, whole square. ये whole square है. Equation 1, RTC by VC minus B whole square is 2A by VC cube. अरे equation 1, 2A by VC cube, RTC, yes, this is equation 1. So you put the value of VC here. So RTC by VC is 3B. 3B minus B is 2B. VC is 3B. 3B minus B is 2B. 2B whole square is 4B square. As there is no space, directly I am writing VC is 3B. 3B minus B is 2B. 2B whole square is 4B square is equal to 2A by VC. What is VC? 3B. लेकिन 3B का whole cube. 3B का whole cube is 3 3 9 3 27B cube. It is 27B cube. Let me check sir. तो B square B गया और कुछ बचा है सर? No. So A will be equal to, if I want A, it will be 27 RTC. I bring 27. 27 RTC by 4. There is 2 here. 2 इधर लाना. 8. So please observe. And there is one B left. B square यहाँ पे B left है. तो it is B here. I repeat sir. B square B cube का मतलब यहाँ पे B बचा है. Take B to this side. RTC B. Okay. RTC B. और क्या बचा है सर? 4 बचा है. 2 इधर आएगा. Yes. A is equal to 27 RTC B by 8. A is equal to 27 RTC B by 8. Correct na? And V is equal to 3B. Let me check sirs. V is equal to 3B. कहाँ गया? V is equal to 3B. कहाँ गया? कहाँ गया? V is equal to 3B. Yes, VC is equal to 3B. Excellent sirs. VC is equal to 3B. अब देखो. P plus A by V square, अगर critical point पे दिख रहा है, into VC minus B is equal to RTC. Excellent. So अब देखना sir. Now PC plus A by VC square is equal to RTC by VC minus B. Okay. So therefore PC plus A. What is A? What is A? 27 RTCB. A is 27 RTCB by 8, but there is VC square also. I repeat, sirs. A 27 RTCB. A 27 RTCB by 8. By there is VC square. But what is VC 3B? तो इसको हम VC square can be written as 9B square. तो इस VC square को I will write this as 9B square. 9B square. Excellent. Is equal to RTC by VC is 3B minus B. So therefore PC is equal to, कुछ कैंसिल होगा क्या? B कैंसिल होगा सर. और कुछ और 8 into 9, it's not 89. कंफ्यूज मत होना सर. कंफ्यूज मत होना सर. यहाँ पे 8 है into 9B square. ये 9B square has come from this 9B square. तो 3 ones 9 ones 9 threes. तो P plus 3RTC by 8B. 3RTC by 8B is equal to RTC by 2B. Okay. So therefore PC is equal to RTC by 2B. RTC by 2B minus 3RTC by 8B. So PC will be equal to, यहाँ पे 4 से मल्टीप्लाई करना. 4 2 से 8 4. 4 minus 3 is 1. So it will be RTC by 4 minus 3 1. 4 2 से 8. तो 8B. Should be correct I think. एक बार चेक करो. एक बार चेक करना सर. एक बार चेक करो. 4 RTC. Correct. This is PC. Wonderful. So now let us calculate, my dear students, let us calculate the compressibility factor for Vander Walls gas. We got PC. We got VC. What is PC? RTC by 8B. Excellent. देखो what is at the critical point, what is compressibility factor? PV by, देखो ऑलरेडी आई हैव गिवन बाय एन आर बार टी, एक बार देखना, सी द कंप्रेसिबिलिटी फैक्टर इक्वेशन, माय डियर स्टूडेंट्स, सी द कंप्रेसिबिलिटी फैक्टर इक्वेशन, इधर देखो, सी द कंप्रेसिबिलिटी फैक्टर इक्वेशन, सो पीवी रियल बाय एन आर बार टी, 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 तो पीवी ये तो रियल है, ऑल आर रियल, पीवी बाय एन आर बार टी, दिस इज कंप्रेसिबिलिटी फैक्टर, बट आई वांट कंप्रेसिबिलिटी फैक्टर एट critical point. I want PV by NR bar T. I want at critical point. What is compressibility factor? PV real by NR by T. But I want at the critical point. Therefore, critical point. तो देखो एक बार, P RTC by 8B. P का value. VC is 3B by NR bar TC. NR bar TC. R bar TC. इनको 1 ले लेंगे हम. अरे मोलार ले लेना रे. मोलार, एवरीवेयर आई टुक इट एज 1, सो वो नहीं आएगा, एवरीवेयर आई टुक इट एज 1, वो नहीं आएगा, ये गया। तो कंप्रेसिबिलिटी फैक्टर फॉर वैंडर वाल्स गैस एट क्रिटिकल पॉइंट इज 3/8 एंड 3/8 आई थिंक 0.375 कुछ आ रहा है, 3/8 एक बार देखेंगे, यस 0.375, एक्सलेंट माय डियर स्टूडेंट्स। So this is the compressibility factor for Vander Walls gas at critical point. So hope you have understood everything, and now in the next class I'll be talking about law of corresponding states, reduced pressure, reduced volume. So what is the reason for developing reduced pressure, reduced, physically I'll explain. So what is reduced pressure, what is reduced volume, what is reduced temperature, and why that reduced conditions are used. So there are so many compressibility factor graphs. I'm converting all compressibility factors, compressibility factor graphs into a single graph. That we call it as reduced pressure, reduced temperature. All these I'll be discussing along with numericals in the next class. Please, if you have understood, kindly share in the form of comments. ऐसे questions करवाऊंगा sir, ऐसे questions करवाऊंगा. So I don't want this video to be so lengthy. It's a humble request. So please watch completely and do not forget to share your views. Thank you. God bless you.